Hi there, in this video I'll be talking about section 4.6 on completing the square. So one thing we want to have in the back of our head is if we notice perfect squares, we can solve quadratic formulas without having to go through all of our factoring steps. So for example, in this equation here, certainly we could try to set one side equal to 0, but we might notice that x squared minus 6x plus 9 is a perfect square. If I take x minus 3 times x minus 3 and FOIL that out, you can check that what you get after combining like terms is x squared minus 6x plus 9. So what we really have is that the quantity x minus 3 squared is what's on the left-hand side. That's equal to 25. Well, if something squared is equal to 25, that something is 5 or negative 5. Don't forget that plus minus. Usually the positive is obvious, but there could be a negative number as well. And this is just our shorthand for two different things. What this really means is maybe x minus 3 is equal to 5. That would make sense. Or maybe x minus 3 is negative 5. That also makes sense. And we can solve these separately. X could be 8, or x could be negative 2. And let's make a note again that plus minus is important. When you're taking the square root, maybe you have a positive, maybe you have a negative. So the trick here was we had that perfect square all ready to go. This thing highlighted in green is a perfect square. Through a method called completing the square, we will turn things that are not quite perfect squares into perfect squares. So for this example here, we might notice that x squared minus 6x is almost what we had before. What we had before was x squared minus 6x plus 9. Well, I just added 9 to the left-hand side. I'd better add 9 to the right-hand side as well. So what we have here is x squared minus 6x plus 9 is equal to 100. As before, our left-hand side is the quantity x minus 3 squared. That's 100, which luckily is a perfect square here. So x minus 3 is either 10 or negative 10. That's the square root. So maybe x minus 3 is equal to 10. Maybe x minus 3 is equal to negative 10. Bye-bye. And there are two solutions. Just had to pause for a moment because someone was coming into my office. So this is an example of completing the square. We added that 9 to each side of the equation, knowing that we would have a perfect square on the left, which makes things very easy. We didn't have a perfect square at the beginning, but we created one. That is called completing the square. Now, to get good at this, we want to notice some patterns in terms of what perfect squares look like. So x minus 1 squared. Wait, that means x minus 1 times x minus 1. Make sure you FOIL these out. A popular mistake is to say like, oh, x minus 1 squared is just x squared minus 1 squared. That is wrong, wrong, wrong. FOIL this out, and you would get that this is x squared minus x plus 1, which simplifies to x squared minus 2x plus 1. Do that for these. Hit pause on this video and FOIL out x plus 7 squared, x minus 4 squared, x plus 10 squared, x plus 6 squared. So I will assume you've already done that. This one should work out to x squared plus 4x plus 49. This one should work out to x squared minus 8x plus 16. This one should work out to x squared plus 20x plus 100. This one should work out to x squared plus 12x plus 36. And there are patterns here. So what we'll notice is that this number here that we're getting as the coefficient of x is always twice as big as the number we had after the x in parentheses. And then this number at the end is the square of the thing we had in parentheses. So basically, we double the green thing to get the yellow thing. We square the green thing to get the orange thing. So we can actually figure out how to get from this number to this number. We take half of it to go with butts back here, and then we square it. Half of 8, half of negative 8 is negative 4. Square it, that's 16. Half of 20 is 10. Square it, that's 100. Half of 12 is 6. Square it, that's 36. So the rule here seems to be take half of that coefficient of x and square it. So here it is expressed somewhat abstractly as a key concept. We can form a perfect square trinomial by starting with this thing, x squared plus bx. And the idea is we take half of b over 2, and square it. We add that to each side. So I added that thing, b over 2 squared, and I will get a perfect square of the form quantity x plus b over 2 squared. So as an example, here, I'll do the second one as an example. Half of negative 14 is negative 7. Negative 7 squared is 49. If I add 49, I have created a perfect square. I've created quantity x minus 7 squared. So hit pause and try that with the other 3 right here. So for this first example, you should be adding 9. Half of 6 is 3. 3 squared is 9. That's the same as quantity x plus 3 squared. For this one, half of 8 is 4. 4 squared is 16, so we add 16. That creates quantity t plus 4 squared. This last one's a bit of a trick. Half of 3 is 3 halves, and if you square that, that's 9 over 4. There's no law that says it's always going to be a whole number. And this is y plus 3 halves quantity squared. Well, why do we care about this? We care about this because it lets us solve equations. That's what we saw earlier on. We can solve equations without all the factoring stuff if we notice how to use a perfect square. So here are the steps presented somewhat abstractly. We want to rewrite the equation as x squared plus bx equals c. So if there's a coefficient in front of x squared, you want to divide by it. If you have a constant, you want to move it to the right-hand side. Then we complete the square by adding that appropriate thing, b over 2 squared. Then we factor, and the factor will create a perfect square. Right? You should be expecting a perfect square. We take square roots, remembering the plus minus, and then solve for x. Break it up into 2 solutions, right? 2 equations, one for plus, one for minus. So let me just show you an example. Just watch this one. We will solve this equation, 2x squared plus 12x minus 4 is equal to 0. And I will follow those steps. So I just want x squared plus something x all by itself. I might notice right away I have a coefficient of 2 here. I don't want it. I'm going to divide everything by 2. If I divide everything by 2, I get x squared plus 6x minus 2 equals 0. And to successfully complete the square, I don't want that minus 2 there. I'm just going to add 2 to each side to get that out of the way. Now I'm ready to complete the square. I look at this number, it's 6. Half of 6 is 3. 3 squared is 9. So I will add 9 to the left. If I add 9 to the left, I'd better add 9 to the right. On the left, by design, I have a perfect square. If I've done this correctly, it will definitely be a perfect square. On the right, I have the number 11. So this means x plus 3 is the square root of 11, or negative square root of 11. For some of these problems, we won't have nice square roots. So we're just going to leave this as root 11. Later on, you can put it in your calculator for an estimate, but we're going to focus on the exact values. So this is an abbreviation for two equations. It's saying maybe x plus 3 is equal to the square root of 11, or maybe x plus 3 is equal to the negative square root of 11. So x might be root 11 minus 3. You could put that in your calculator. It's going to be something like 0.4. Or maybe x is negative root 11 minus 3. That's going to be something like negative 6.4. These are our exact solutions. Always get exact solutions, and then if you are motivated to do so, you can simplify them. So with this as an example, and rewatch it if you need to, go fast in the videos knowing you can pause and rewatch. Using this one as an example, try this one. Solving 3x squared minus 12x plus 6 equals 0. Hit pause and give it a try. So I will assume now you've already tried this. I don't like that 3. I'll divide everything by 3. And I don't like that 2. It makes completing the square harder. So I'll subtract 2 from each side. Now I can complete the square. Half of negative 4 is negative 2. If I square that, that's 4. So I'll add 4 on both the left and the right. Remember to do it on both sides. This is quantity x minus 2 squared, and this is 2. So x minus 2 is either the square root of 2 or the negative version. I'll write them as two different equations. Oh, this should be a 2. So x is root 2 plus 2, and that's about 3.4. Or x is negative root 2 plus 2, and that's about 0.6. We're getting answers we couldn't have gotten by factoring. Factoring doesn't produce these irrational radical expressions. So this is a method that's a little more powerful. Okay, so one last thing we can do here is we can take a quadratic that is in standard form and use completing the square to put it in vertex form. I'll tell you right now, I elaborate on this with harder examples in a different video and an addendum to these notes. But here is a simple example. Let's just remember, vertex form looks something like this. It's a way of writing a quadratic where it's more obvious how we shifted things, and that's helpful for knowing what the graph looks like. So what I'll do here, right, we have y on the left-hand side, and I don't want to change that. So here we're going to not change the value, but change the appearance. I'm going to leave a little space here. There's definitely a minus 6, but I want to think of that minus 6 as far away from this stuff. And I'll complete the square. Half of 4 is 2, 2 squared is 4. Adding 4 completes the square. But I can't just add 4, right? I'm saying this is y. I can't just add 4 to y and say it's the same thing. So I will immediately subtract 4. So there's a little trick here. I add and subtract the same number. Why? Because I want to get a perfect square in here. And I will notice that those first 3 terms, by design, create a perfect square. So what I have here is y is quantity x plus 2 squared, from noticing that that's a perfect square. And then afterwards I have minus 4 minus 6, that's minus 10. So this is in vertex form. This tells us about the transformation. If we wanted to graph this, it would be much easier than the original version, because this would be like our standard parabola x squared. But this is telling us we've shifted it 2 units to the left. This is telling us we've shifted it 10 units down. So it would have a vertex at the point negative 2, negative 10, and our parabola would look something like so. from the original form, it was not at all obvious where the vertex was, so graphing this might not be all that helpful. But by doing a little bit of work here, we're able to switch it around. And I just have a note here, whenever we manipulate an expression by adding or subtracting, we have to keep things true. So either we add or subtract the same thing on both sides of the equation, or we did what we did here, which was add and subtract the same number on the same side of the equation, so that we didn't actually change the value, we just changed the form. All right, that is it for this video.